So, in this short video, we are going to explain Riemann's extension theorem. So I will follow the notation in my book. So let's have this Cn 0, a neighborhood of 0 and Cn, and then we have a variety, germ of an analytic variety here, and let's use this notation, this being x. So this is a proper analytic variety. It means that it is given by at least one non-zero holomorphic function, or in its ideal we have at least one non-zero holomorphic function. And so if f just a moment. So if we have a holomorphic function for x, y to c, in general it will not extend, but if we assume that f is bounded, so it means that it doesn't go to infinity, so this will imply that f extend to a holomorphic function in X. Okay, so the proof is in order to prove the theorem, we first use the fact that this y is proper. Let y a subset of G equal to 0, G holomorphic. And G being holomorphic, and then as we can assume that G is regular at Zn. I didn't make definition, but this means that G0 Zn not identical is 0. And remember that these are n minus 1 coordinates. And yeah, at the end of the day, this f is not defined in G equal to 0. So remember that in the Weierstrass preparation theorem, we could take z line, and then the zeros of G equal to 0 was z line, and then z1, z1 m, z2 m, and so on. So again, in the case similar to the case of in the case of Weierstrass preparation theorem, we will take this circle. So the idea is that to avoid z1m, because my f is not defined in z1m. Anyway, z prime very close to 0. Then z1m, z2m will be close to 0 also. So this means that at the end, I can start integrating over this guy. And I can define f tilde in this way. And f tilde is going to be, first of all, f tilde is a holomorphic function in the whole variable z. And this is a holomorphic function in Cn0, because f is, it is holomorphic in Zn because Zn just appears inside the integrand, and it is holomorphic in Z prime because f itself it is. And the next is that we have to show that f tilde is equal to f, and the reason is that when we fix Z line, Z prime, then this is this becomes a holomorphic function in one variable, and it is it is holomorphic outside this finite number of points, and it is bounded. So this the same theorem of Riemann extension theorem in one variable we have it. It will imply that f extend to the whole disks. So it is actually uh, holomorphic in Z1M, Z2M. So then we will apply the Cauchy formula in one variable, and then we will get f tilde equal to f. So the main idea is to use the same theorem in one variable case. So if you have a one variable function, holomorphic function, holomorphic outside a point, and bounded around that point, then it will be holomorphic at that point. And so this is the theorem. So the first corollary of this theorem is that Cn 0 minus y is connected. And this is somehow different from the real analysis case, because we know that, for example, S sphere in R3 divides R3 into two pieces. But in a complex world, just zeros of function, they do not divide. And also this the proof just follows from the previous theorem. So it is if it is not connected, then we define f if it is not connected, so it has at least two connected pieces. Let's say we write in this way, u1 and u2. Then this u1 and u2 will cover my space. This was x minus 1. So it might have more connected components. So let's just put u1 and u2, the union of connected component. So just define f equal to 0 in u1, f equal to 1 in u2, and this does not extend, doesn't extend to what? To what? Because in any case, so from u1 and u2 we can approximate points in y. From one side we can approximate by 0, by the values of that points are 0. From another side, approximating the values of f are 1. So there cannot be evaluation of f on the points of y itself.